Hey guys, thank you for joining my video about the worksheet from last Wednesday's session, which was April 3rd. I'm going to walk you guys through every reaction we have and then show some of the mechanisms if they're needed. So with our first one, we have addition of H2. H2 meaning there are two hydrogens. PD cat meaning this is palladium. Cat meaning catalyst. And also instead of PD you can use platinum or nickel as well. It's a fun fact, I don't know. One important thing about this is that this is syn addition, meaning whatever you're adding across the alkene, which in our case is or are hydrogens, they're going to be added on the same plane. So this one's pretty straightforward. All you really do is you're turning a alkene right here to an alkane, because once you add both hydrogens on both sides of the alkene, you're going to get that, right? And that's all. So takeaway from this is used to turn an alkene into your alkane, alright? Next one's a little bit more complicated. Not more complicated, but a little bit more complex. This one's called acid catalyzed addition with concentrated H2SO4 in heat. H2SO4 is also known as sulfuric acid. It's very nasty stuff. And then some important things to know. This reaction is Markovnikov, or it follows the Markovnikov rule, meaning whatever you add across your alkene right here will be added to the more substituted side. Meaning if we look at this alkene, we see that it has two sides, correct? And then I want you to count the runoffs or carbon offshoots on each side of the alkene. What I mean is if we start on this side, the left side, we see that there's one runoff, and that's it. And if we go on the right side, right here, we also see that there's one runoff of carbon chains. Another thing to know is this is non-stereospecific, meaning that it can be added syn, anti, both, it doesn't really matter. So H2SO4, I'm going to draw that out for you guys. You don't have to draw this out every time, but I just want to draw it out so you guys know what it looks like. Oops. There you go. Boom. Sulfuric acid, and then I'm going to draw out the structure that we're going to react it with. And then I think it's easier if I draw out the mechanism for this, so you guys can see what's going on. Alright, so our nucleophile is going to be our alkane, or our alkene, and that's going to pluck off a hydrogen off of sulfuric acid. So what I do is I'm going to start the back of my arrow on this alkene and draw it to where I'm plucking. So I'm plucking that hydrogen, and then the bond in between hydrogen and oxygen right here snaps back to oxygen. And I'm going to make sure I draw my lone pairs, just so you guys know what's going on. I'm going to draw an arrow, and then redraw this structure right here as this. So I'm going to add the hydrogen either here, or I could also get this hydrogen down here. Okay? I drew it on both sides because, remember, this reaction is Markovnikov, like I said right here, meaning our product or whatever is going to get added to the most substituted side of the alkene. But in this case, both of them are equally substituted, so we're going to get a mixture of both products. So right here, I added a hydrogen across, but because I broke that alkene right there, I'm going to also have a positive charge because we stole from that carbon. This is also known as a carbocation. So I redrew our first structure right here as these two. Now I'm going to redraw this. So you're going to have oxygen with an extra pair of electrons. That's why it has a negative charge. And then the rest of our sulfuric acid structure. Okay. Alright, from here, you have your nucleophile, which is our O minus right here. And then we have an electrophile, which is our carbocation. So I could redraw, here I'll just do this so it's easier for you guys. Copy, paste, copy, paste. Perfect. So from here, all you have to do is take your nucleophile and attack your electrophile, which is right there. And we do the same thing on this side. Alright, so our products are going to be this. And this. Okay, and that's it. Problem letter C. You have your structure interacting with peracetic acid. The mechanism with this is a little tricky, but all you have to really know is that peracetic acid adds an epoxide across your alkene. And an epoxide is basically an ether in a ring, also known as a cyclic ether. That was one of the functional groups that y'all learned in the first few weeks of Orgo. Ether is just this. So an oxygen in between two R groups, or two carbon chains. All right, so I'm going to redraw my structure. Boom, boom, boom. That. Oh, didn't mean to do that. So when you add your epoxide across your alkene, you're just going to draw this, and that's it. And one thing to know is that there's a lot of strain in here because the ring is so small, as opposed to a normal cyclohexane, which has a lot less strain than your epoxide on the left. Letter D, acid catalyzed addition, or something analogous to that. Two things about this reaction that you need to know. This is Markovnikov, and this is non-stereospecific. Markovnikov means we're going to add our group across the most substituted side of the alkene, which in this case is the right side, because there's two carbon chains as opposed to one carbon chain. This also is non-stereospecific, so you can get both syn and anti-addition of your group that's being added. So I don't think I need to draw out the mechanism, but I want you guys to understand all the products that we have. So I'm going to add an alcohol across the most substituted side. So that's going to be on the right side like this. But also because we can always get a mixture of products, I'm going to get an alcohol on the left side of our alkene as well. Okay. But in this case, you see that this carbon is a chiral center, because if I look closely, we have 4 different groups, right? Off of this chiral center. See that OH is one group, hydrogen is another group. And if I go left and right, we see that the left keeps on going there, but the right breaks into 2 chains. So we have 4 different groups, so that's a chiral center. And if we have a chiral center, we're going to have addition of alcohol on both wedge or the dash. Okay. In the answer key, he has this carbon, or this methyl group, as a wedge, I think. Let me check. No, he has another dash. But if you do a wedge, just keep it a wedge. Or if you do dash, keep it a dash. Just keep it the same across the board. But you might ask, which one is our answer? All of them are your answer, but the correct answer is this. This is your major, because your alcohol group is added on the more substituted side of that alkene. And these are your minor products. Okay. Okay, letter E. This one is called hydroboration oxidation. 2 things to know that are important about this reaction. This is anti-Markovnikov, meaning your group that's added is going to be added to the less substituted side this time, rather than Markovnikov, which is the more substituted. Another thing to know is that this is syn addition, meaning they're going to be added on the same plane. So whatever is being added, in this case an OH group, is going to be added on the same side as your hydrogen. So I believe the mechanism for this is a little complex as well. So I'm just going to draw your product. I will make another video if you guys want about certain mechanisms. So just let me know. Okay. Our alkene right here, right? Which side of the alkene, this side or this side, is more substituted? I'll give you like 5 seconds. Okay, time's up. Trick question. Both sides are the same amount of runoffs or substitutions. So you can add your alcohol on either side. So I'm just going to pick the top side. So alcohol can be added here. Your hydrogen will be added here. Actually, I did that wrong. You can do a wedge or a dash. Just make sure that if you do one or the other, it's the same for both. Okay. And that's it for that. Quick review. Hydroboration oxidation is adding an alcohol group and a hydrogen across your alkene. It adds your alcohol to the less substituted side. And both groups are added in the syn addition, meaning they're going to be on the same plane as each other. Either both are wedges or both are dashes. Letter G, HBr with catalyst peroxide. Remember, R just means that it is any carbon chain. Alright, so one thing to know that's important about this is that your bromine in this case is going to be added to the less substituted side, also known as anti-Markovnikov. So I'm going to redraw as that. And then our less substituted side of the alkene is the bottom side as opposed to the top side, because the top side has 1 carbon runoff, but the bottom side has no carbon runoffs. Okay, so Br is just going to go right here, but you also get this right here, the more substituted side. Jack. Sorry. I'm going to redraw. Br is going to get added there as well. But this reaction says it's anti-Markovnikov, so that's going to be our major product. So this is our major product. This is our minor product. Letter H. Br2 across your alkene. This is also known as halogenation or halogenation. I don't know. Either way, the important thing to know is that halogenation is anti, meaning your BRs are going to be added across the alkene opposite to each other. What I mean is one is going to be on a wedge and the other is going to be on a dash. Alright? Do you want to draw out the mechanism for you guys? Boom, boom, boom. Okay. Alright, so this guy's weird. Your alkene is going to be your nucleophile attacking this Br, but also that Br wants to attack your alkene. Like, what the heck? What's going on? I don't know what's going on either. It's just how it is. From there, the bond in between your BRs goes back to the second BR. I'm going to redraw. Boom, boom. Alright. I'm going to have this BR on 2 wedges. Alright. B R minus. Alright, so this cyclic Br right here, Br in a ring, is called a bromonium ion. So from there, your Br minus is going to attack one of these carbons, and the carbon in between the carbon that was attacked and your Br is going to go back to Br like this. I'm going to redraw. Oops. that's it. One thing to know is you might be asking, why is this on a wedge? Like I said, this reaction is anti, meaning if this bromine right here is on the wedge coming at us, this bromine can't come in from the front and attack, so it has to come in from behind. So that's why when it comes from behind, it ends up on the dash, like that. Letter I. This structure reacting with O3. I don't know what this is, but I'm going to try my best. So, I think the trick with this is to number your carbons, like that. Okay. And the key with this is that this causes your alkene to be split in half like this. So we're going to take a knife, cut the alkene here, and our ring is going to open up. I'm going to redraw like this. So, boom, boom. Actually, boom, there. 1, 2, 3, 4, 5, 6, 7. Okay. So I'm going to number again so we can keep track. And the thing with this is that you're going to add a carbonyl group to the 3 carbon and your 7 carbon. So what I'm going to do is this. So carbonyl right there, and then carbonyl right here. And that's it. You just split your alkene, you number, and then whatever number is on either side of this cut is a carbonyl which is added. So what I mean is 3 carbon over here has a carbonyl. 7 carbon over here has a carbonyl. And that's it. Letter J. HCl with our structure right here. I believe the name of this is, let me see, hydrohalogenation. This is not a mouthful. Hydrohalogenation. Alright. I'm going to cut this carbon off right here so I don't have to redraw the whole structure. So I'm going to do blah, 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 that, HCl. Okay. Alright, so you guys should be pros at this by now. Alkene attacks the hydrogen right here. Bonding between hydrogen and chlorine goes back to chlorine. Now you can redraw. Oops, yeah, redraw like that. Hydrogen can either go there, or you can get, you can get this as well. Hydrogen there and carbocation there. You'll be asking, why am I drawing both? It's because we're going to have a major and a minor product. And obviously the major is going to be the answer that your professor wants. So from here we have Cl minus in solution. I would draw it twice, but I'm just going to draw it once. It as in Cl minus for sake of time. Cl minus is going to attack carbocation here. It's going to also attack here. One Cl minus doesn't do both, it's just that I don't want to draw both. So the top reaction is going to look like this. Okay, and then your bottom reaction is going to look like this. Alright, the top one's going to be your major, the bottom one's going to be your minor. Alright, so in this case, this is Markovnikov. I forgot to mention 2 very important things. With hydrohalogenation, this is Markovnikov, meaning our group is going to be added to the more substituted side of the alkene, which is here. And then this is non-stereospecific. So we're not going to have syn versus anti, we have both. That's why we have major and minor.